Hello, everyone. I hope you had a chance to review the concepts from our last session. So to recap, we were exploring regenerative vapor power systems and focus specifically on the open feed water heater. So let's remember the big picture. The reason we introduced any modification to the basic Rankine cycle, whether it's reheat or regeneration, it's to increase the thermal efficiency. So regeneration does this by using high quality steam extracted from the turbine to preheat the feed water before it enters the boiler, right? Thereby it raises the average temperature at which heat is added to the cycle. So the open feed water heater is an effective way to achieve this increase in thermal efficiency through direct contact mixing, right? But this mixing imposes a strict constraints, which is the extracted steam and the feed water must be at the same pressure to allow them to combine, often necessitating a complex pumping arrangement. So today, we shift our focus to the second primary method of regeneration, which is the closed feed water heater. So the closed feed water heater is similar to open feed water heater, but the primary difference is that there is no direct mixing. So basically, the closed heater serves the exact same purpose to preheat the feed water, but it achieves this functionality through a fundamentally different mechanism. As we will see, it operates as a shell and tube heat exchanger, where the feed water and extracted steam streams do not mix. Okay, so this stream isolation gives us a crucial design advantage. The two fluids can be at different pressures, which was not the case for direct contact mixing or open feed water heater. So this difference impacts how we design the entire power plant, particularly how we manage the condensate. So while the open heater simplifies heat transfer through mixing, the closed heater offers greater pressure flexibility through heat exchange. So we'll start our discussion by examining the construction of the closed heater and the two primary methods for handling the condensate. So let's look at a schematic for closed feed water heater, which we have here. We have diagram A and diagram B. So these closed feed water heaters are crucial components in modern Rankine cycles because they enable regenerative feed water heating, which is a key method for significantly improving the overall thermal efficiency of the power plant. So the underlying principle here is to use a steam that is basically bled or extracted from the turbine, which would otherwise produce work, to preheat the feed water before it enters the main steam generator or boiler, right? So later we're gonna integrate this the closed feed water heater into the cycle. But first we wanna look at it separately. So by doing this, we raise the average temperature at which heat is added to the cycle, leading to that crucial boost in efficiency. Now let's look at the construction. Closed feed water heaters are structurally classified as shell and tube recuperators. So take a look at the diagram here. So the main feed water, the working fluid we are trying to heat, basically this stream, flows inside the tubes. Okay, these are called the tubes. So you can see the feed water in and feed water out in this diagram. So the hot extraction steam flows on the outside of these tubes. So this is called the shell, and this is a tube, and the extraction steam is basically flowing on the outside of these tubes. So as the steam flows around the tubes, it condenses, and in the process of condensing, it transfers its latent heat to the feed water flowing inside the tube, okay, causing the feed water temperature to increase. So a major advantage of this design is that it ensures stream isolation. So since the feed water and extracted steam do not mix, they can operate at different pressures. So which is in contrast to the case of open feed water heater where mixing happens and we need to have the same pressures. So this provides a lot of flexibility in power plant design compared to open feed water heaters, where, as I said, the streams must be mixed at a common saturation pressure. So finally, for this slide, let's look at the fate of the condensate. So the liquid that is basically formed from the extracted steam at the bottom of this shell is called the condensate. We have two primary ways of handling it, as shown in the diagrams. So condensate pump forwarding is the first approach, which is this diagram A. So here the condensate is collected at the bottom and then sent through a small pump, which you see here. So the pump increases the condensate's pressure and directs it to a higher pressure line. This is typically the main feed water line after the closed heater, rejoining the total flow at a high pressure point in the cycle. So this method recovers the condensate at a high pressure, minimizing the work the main boiler feed pump has to do later. So the second approach that is shown in this diagram is condensate trapping. So here the condensate is sent through a steam trap. So a trap is essentially a valve that only permits liquid to pass through a region of lower pressure. So in this case, the liquid is allowed to expand through the trap here to a lower pressure heater or condenser, which we'll discuss later. So this expansion is a throttling process, meaning that it's constant enthalpy process. And while it's simpler as it avoids the extra pump shown in this diagram A, it's also an irreversible process that slightly increases the cycle's entropy generation. So the enthalpy is constant because, as I said, this is a throttling process, but this is an irreversible process, which means that entropy is going to increase here. So we will see how both these approaches are integrated into full Rankine cycles in the slides to come. But for now, remember the core concept here, a closed non-mixing heat exchanger using extracted steam to preheat the feed water is called a closed feed water heater, which is going to increase the thermal efficiency of the Rankine cycle. So now let's discuss how we manage the condensate in a closed heater. So following up on our introduction to closed feed water heaters, we want to talk about a critical operational aspect, and that's how do we deal with the condensate. So remember, the whole point of a closed heater is to condense the extracted steam, So we are left with this high purity liquid water, which we call the condensate, that needs to be returned to the cycle efficiently. Remember that we are using a thermodynamic cycle for this Rankine cycle, and we need to recover this basically water that we have generated here using the extracted steam that comes from the turbine. So there are two primary methods for condensate removal. So as I said, the first method is pump forwarding, in which we use a small pump that increases the condensate pressure and then forwards it to a high pressure point in the cycle. Typically, this point is the main feed water line after the closed heater, or sometimes another component operating at a higher pressure. So this method is advantageous because it recovers the energy and high purity water at an elevated pressure, which minimizes the pumping work required by the main boiler feed pump later in the cycle. And the second approach, as we discussed, is trap draining, which is basically a simpler option to allow the condensate to expand through a trap. This trap then directs the fluid into a feed water heater operating at a lower pressure or directly into the condenser, as we will see. So this expansion through the trap is an irreversible throttling process, which means that we have a drop in pressure without any work output, but it avoids the cost and complexity of an extra pump. So the steam trap effectively separates the condensed liquid from any remaining uncondensed steam. So this brings us the key function of this component, the steam trap. Basically, a trap is specifically a type of valve designed to permit only liquid to pass through. Its operation is based on the density difference between the liquid and vapor. It holds back steam, but lets condensate pass to a region of lower pressure. So by preventing a steam from passing through, the trap maximizes the heat transfer inside the heater and ensures that only liquid, the condensed steam, basically, is sent to the lower pressure part of the cycle. So in power plant design, the choice between these two methods, basically pump forwarding or trap draining, is based on a complex economic analysis that balances the cost of the extra pump that we need here and its power consumption against the thermodynamic losses associated with the irreversible throttling process of the trap. So we will see the trap draining method used in our next cycle diagram as it offers a clean common loop configuration. Okay, now let's integrate the closed feed water heater concept into a complete cycle diagram. So this diagram on the right shows a regenerative vapor power cycle that features one closed feed water heater that is shown here. So notice this specific configuration uses a trap draining method. So we have a trap here, a steam trap, as we discussed earlier. So where the condensate is basically trapped directly back into the condenser, okay, here. So let's quickly review the major assumptions and then trace the flow, paying close attention to the TS diagram at the bottom right here, which visually represents the entire process. So first, the idealizations for our analysis. Basically, we assume isentropic processes through the turbine stages that are shown here, 1 to 2 and 2 to 3. As you see, we have vertical line on this TS diagram, meaning that entropy remains constant. And for the pump work from 4 to 5, the specific entropy basically here remains constant. This assumption gives us the upper bound for the cycle's performance, basically. an ideal Rankine cycle, as you saw previously. We also assume no pressure drops accompany the flow through any component here. So the pressure here for the boiler section is constant, for example. And the pipes and the steam generator, the condenser, or the feed water heater operates at constant pressure, except the pressure drop that we have here for this trap, state 7 to state 8. As you see, we are moving from this pressure line to this pressure line. So this process basically is irreversible, and we are basically generating some entropy. Entropy is being increased here. So this is an irreversible process. Now let's trace the flow path. So turbine inlet, state 1. The cycle begins with the total mass flow rate of 1 here, or m dot, which we denote as basically this 1 in parentheses. So exiting the steam generator as superheated or sometimes saturated vapor at its highest temperature and pressure. So here, as you see, state 1 is superheated vapor. And then we have this first turbine stage, which is state 1 to 2. This total steam flow, this 1 in parentheses, expands isentropically through the first stage of the turbine, generating this work W dot T for this first stage of the turbine. And then we have this steam bleeding here at the state 2. Basically, a fraction Y of this flow is bled or extracted and diverted to the shell side of the closed feed water heater. This is the process that gives the cycle its regenerative nature. So the remaining flow here from 2 to 3 basically continues expanding through the second stage of the turbine until it reaches the condenser pressure at the state 3. So this fraction 1 minus Y is what ultimately enters the condenser here, where it's cooled and condensed, rejecting this Q dot out. Okay? So remember here, the mass flow rate for the second stage turbine is 1 minus Y. For this first stage, the mass flow rate is 1. So in the next slides, we'll follow the two separate streams, basically the main flow and the extracted flow here, as they move through the rest of the components and see how they are rejoined. Okay, now we left off with the main flow, 1 minus Y, heading toward the condenser, and the extracted flow Y here heading into the closed feed water heater. So let's trace the journey of the extracted flow and see how it rejoins the main cycle. So this state 7, which is shown here, the extracted steam Y, which enters the shell side of the heater at the state 2, right, transfers the heat to the feed water inside the tubes and condenses. So it's important to note that the condensate, now a liquid, exits the heater at a state 7. So here is the state 2, and here is the state 7. So you see the pressure is the same because this is basically the same stream here. And this is another stream within this shell. So this is the same stream. So the pressure at the state 2 is equal to pressure at the state 7. So here, basically, the heat transfer is assumed ideal in our analysis. Basically, the condensate leaves as saturated liquid at state 7, as you see here. And the pressure is the basically extraction pressure, same as state 2. So on the TS diagram, this state 7, as you see, lies on the saturated liquid line here, corresponding to the extraction pressure. This condensate trapping that happens from state 7 to state 8 is shown using this dashed line. So as we discussed, the traps function is to let the liquid pass into a region of lower pressure. So this has a lower pressure than this. So then in this case, the condensate is trapped into the condenser. So basically, we are passing this condensate to the condenser. So by doing this, the flow Y that you see here, basically this stream here, this flow Y effectively reunites with the main flow 1 minus Y, right? And then the result is again 1. So here is again 1, this is Y, this is 1 minus Y, they add together and they produce this 1 unit of mass flow rate. Okay? So then we have this trap expansion, which we discussed, and this is an irreversible process. This is basically a throttling process, meaning that enthalpy remains constant. And we make the key assumption that basically H7 is equal to H8, enthalpy is constant. And we note that this is not an isentropic process. Entropy increases, even though the enthalpy remains the same. So state 8 lies at the condenser pressure here just before mixing with the main flow. Okay, so here's the main flow, and this is Y, which we extracted here. Here it's being reunited with this 1 minus Y, and we are basically having the same whole mass flow rate, this 1 here. And then also remember that this dashed line represents this irreversible process, meaning that this is not an isentropic process. The total mass flow entering the condenser is the sum of the two streams, the flow from the turbine, 1 minus Y, and the condensate from the trap, which is Y. So the addition will give us this 1. So this trap draining mechanism is key to efficiently returning the extracted steam's energy and mass back to the condenser inlet, ready for the main pump. Okay, this is the main pump. Now let's complete the loop for this regenerative Rankine cycle. We have followed the two streams until they both enter the condenser, right? So this condenser outlet state 4, basically the main flow 1 minus Y and the condensate flow this Y, they mix and condense, rejecting the heat, this Q dot out, and the total flow 1 then exits the condenser at the state 4. Here's the state 4. And as you see, this is saturated liquid at the lowest cycle pressure. So this entire flow 1 is then taken by the main feed pump and pumped isentropically up to the boiler pressure here. And then basically it exits at state 5. So this feed water heater from state 5 to state 6, now at high pressure, enters the tube side of the closed feed water heater here. And as it passes through, it absorbs heat from the condensing extracted steam, which moves from state 2 to state 7. So the feed water's temperature increases significantly and it exits the heater at state 6. Okay, here's the state 6. Notice on this TS diagram that state 6 is a high pressure compressed liquid state. This is compressed liquid, not saturated liquid. And its temperature is much higher than state 5, thanks to the regeneration. Okay, so as you see, the main goal of the regeneration is to increase the temperature of the working fluid before it enters the steam generator. Now, in the steam generator, state 6 to 1, the total mass flow 1 is directed into the steam generator or the boiler. So here the working fluid is heated at constant pressure to return to its initial high temperature state, state 1. And this is as previous ideal Rankine cycle. So this completes the thermodynamic cycle. And the heat added here is Q dot in. So while this cycle introduces complexity, the preheating of the feed water from state 5 to state 6 means that we add basically Q in starting from a higher average temperature, which is what boosts the thermal efficiency. However, in this ideal cycle, we must acknowledge the source of irreversibility, although we assume isentropic pump and turbines here, and no pressure drops in the components. The closed heater, the process of the closed heater itself is inherently irreversible, basically because heat transfer requires a stream to a stream temperature difference. So this is the first stream, which contains steam, and this is the second stream or the main stream, which contains liquid water. So there is a temperature difference between this stream and the other stream. So we call this a stream to a stream temperature difference. And this is a source of irreversibility. So for heat to flow from the condensing steam at the saturation temperature for this pressure P2 to the liquid feed water, so the feed water must remain at a lower temperature. This temperature difference is an unavoidable source of entropy generation within the cycle, which reduces the potential maximum efficiency, or basically exergy. So just remember that addition of this heat or closed feed water heater is going to introduce entropy generation and it's going to reduce exergy. So the next slide is about determining the extracted flow fraction, Y, which we also did for the open feed water heater. So we have now traced the flow through the entire regenerative vapor power cycle. The next crucial step is analyzing the system, basically to quantify the fractions of the total flow at various locations. So we have defined the total flow entering the turbine as this 1 and the extracted fraction as Y, and the flow continuing to the condenser as 1 minus Y. So we must calculate this Y here to determine the work output and the heat input. The fraction of total flow extracted, basically this Y fraction, is found by applying the principles of conservation of mass and energy to a control volume directly around the closed feed water heater. We use a similar approach for the open feed water heater, where again we did a conservation of mass and energy for control volume around the open feed water heater. So this is where the mass flow rates of the two streams are clearly separated and interacting thermally. So let's review the assumptions for this balance equation. So we assume a steady state operation, as always. We assume no heat transfer between the feed water heater and its surroundings. So all the heat transfer is internal. There is no Q dot of CV. So Q dot of CV is 0. So, and we also neglect the kinetic and potential energy effects. So under these assumptions, the steady state energy rate balance simplifies to basically m dot multiplied by enthalpy at the inlets are equal to m dot multiplied by enthalpy at the outlets, right? So if we do this energy balance for this for a control volume around this, for the closed heater, the two mass flows enters and exit. Basically, we have entering mass at this point and this point, and exiting mass at this point, 7 and 6. Okay, and we have flow rate is y here and flow rate is 1 here. So if we do a simple input-output balance here, we see that 1, the mass flow rate 1 multiplied by H5, this is entering, then Y plus, multiplied by H2 is also entering. So 1 multiplied by H5 plus Y multiplied by H2 should be equal to these outlets. Basically, Y multiplied by H7 plus 1 multiplied by H6. So if we move everything to one side, they will equate 0. Basically, Y multiplied by H2 minus H7 plus H5 minus H6 is equal to 0. So H5 minus H6 is the increase in enthalpy of this basically working fluid here. And this H2 minus H7 is the increase in, is the decrease in the enthalpy of this extracted steam. So notice here we have H7 is basically less than H2, right? So this is steam that coming from this first stage of the turbine. So H7 is obviously less than H2. So H2 minus H7 is positive. However, here H5 is also H5 is less than H6 because we are heating this water. So H5 minus H6 is negative. So this is positive, this is negative. They are canceling each other and the result is 0. So this is a simple energy balance. So using this, we can solve this simple equation for this fraction y, and we can obtain this relationship for y. So this equation is critical. It shows that the required flow fraction y is determined entirely by the specific enthalpies at the 4 state points around the closed heater. So the numerator H6 minus H5 represents the heat gained per unit mass of feed water, and the denominator H2 minus H7 represents the heat lost per unit mass of extracted steam. Okay, we had a similar relationship for the case of open feed water heater. Now we have successfully developed the energy balance equation to solve for the extracted flow fraction y. Let's finalize the key assumptions that allow us to use these simple equations and calculate all necessary work and heat terms for an entire cycle. So first, let's revisit the trap expansion that occurs between state 7 and state 8. This is where the condensate from the closed heater, state 7 drops in pressure as it is routed back into the condenser pressure line, state 8. So the throttling process assumption is critical here. Remember, whenever we say throttling process, that means constant enthalpy. So we assume basically enthalpy remains constant, however, entropy is being increased. So the remaining steps for the analysis involves the work and heat transfer evaluation, which is similar to what we did for Rankine cycle in the previous sessions and previous examples. Basically, we need to obtain the work of the cycle, and then we divide it by this heat transfer that is added to the cycle here to obtain the thermal efficiency, right? We're going to do an example, and you'll see how we do this. So, and then I briefly want to describe this use of multiple feed water heaters. So the primary takeaway here is that the thermal efficiency of the regenerative cycle can be continually increased by incorporating several feed water heaters at suitably chosen pressures. So why is this the case? So the goal of regeneration is to bring the feed water closer to the saturation temperature corresponding to the boiler pressure before it enters the boiler, right? So by using multiple stages of preheating, we incrementally reduce the temperature difference between the heating fluid, the extracted steam, and the heated fluid, basically the feed water in each stage. So this minimizes the external irreversibility associated with heat addition and thereby increasing the average temperature at which heat is supplied to the cycle. So theoretically, the more heaters you use, the closer you get to the ideal but impractical Carnot efficiency. Okay? However, theory must meet reality, right? Which brings us to the economic considerations. So the number of feed water heaters used in a power plant is ultimately based on the economic consideration, while each additional heater provides an increase in thermal efficiency. That increase becomes marginally smaller with every new component. So the marginal increase in thermal efficiency must be large enough to justify the added capital costs, right? So this includes the cost of the heater vessel itself, the extensive piping, and also extra valves and any additional pumps needed for condensate management. So basically, this diagram on this slide provides a glimpse into the complexity of a real-world system, which in this case features several closed heaters and deaerating open heater. Notice the integration of different component types. We have open heater here in the middle, which often operates above atmospheric pressure. This specific type of open heater is critical because it allows the deaeration process, basically the venting of dissolved oxygen and other non-condensable gases, which is necessary to minimize corrosion throughout the cycle. So we have closed heaters on either side of the open heater, these closed heaters, basically handling the extremely high pressure side and a lower pressure side. So the main point is that modern cycles are basically careful optimizations, maximizing efficiency through basically multiple stages of regeneration while minimizing the installation and operating cost of all the necessary equipment. So as we established, basically complex power plants use multiple heaters, often a combination of closed and open types to maximize thermal efficiency. Now let's explore why even in a system dominated by a closed heater, a plant with multiple feed water heater will ordinarily have at least one open feed water heater. So this open heater is strategically placed to operate at a pressure greater than atmospheric pressure. The primary reason for this is to facilitate a crucial process called deaeration. This process is essential for the longevity and reliability of the plant. Basically, the main goal of this process is to remove dissolved gases, as I discussed, specifically oxygen and other non-condensable gases from the working fluid. So if you look at the complex diagram on this slide, you can see the component labeled basically the aerating open heater. In this unit, the main feed water flow, the extracted steam, and any trapped condensate flows all mix at a common pressure. This direct mixing ensures that the feed water is brought into direct contact with the steam, which facilitates the flashing of dissolved gases out of the liquid phase. So these gases are then collected and safely vented. So in a sense, while the closed heater maximizes the cycle thermal efficiency, the strategically placed open heater at a high pressure ensures the purity of the working fluid and minimizes corrosion. So it's critical. It's a critical engineering trade-off that balances pure thermodynamic performance with practical operational reliability and maintenance costs. Okay, so this was the discussion for today's session. We'll continue from here on Wednesday.